Hello all, myself Chothe from Kekewag Institute of Engineering Education and Research, affiliated to Savitribai Phule, Pune University in Maharashtra, India. The topic presented is Authenticated Image Encryption using robust chaotic maps and enhanced AES. These are the contents which will be presented. What is the need of soft security? The news presented over here shows that connected banking requires new security protocols to keep the consumer data safe. Image is basically the arrangement of pixels, but traditional cryptographic methods cannot be used for image encryption because it is having high redundancy, bulk data capacity, and also the adjacent pixels are highly correlated. These are all the advanced applications of color image encryption. Cryptography is basically the science of secret or hidden writing. It is used to protect the data against unauthorized access. As shown, it is the symmetric algorithm where the same key will be used for encryption and decryption. It is having main two components, encryption and authentication. The AES algorithm is presented. It accepts the 128 bits blocks and generates the cipher text. Key expansion will be the first method used. Next, initial round, where the addition of round keys will be performed. There will be multiple rounds having substitution of bytes, shifting of rows, mixing columns, and addition with the round key. The final round does not include mixed columns. Chaos theory is the branch that deals with complex systems to generate the output which is highly sensitive to initial parameters. Chaotic map is a mathematical function having chaotic characteristics. The combination of chaos theory and cryptography will produce the chaotic encryption. It is having very important characteristics like determinism, non-linearity and unpredictability, pseudo-randomness, and sensitivity to parameter changes. So as it is appearing to be random, but actually it is having the order and pattern. Why to include AES with chaos? AES GCM is the Galva counter mode of operation of Advanced Encryption Standard. It is having advantages of immunity to statistical attacks, lower peak signal to noise ratio, and more difference between histograms of input and encrypted images. The advantages of chaotic maps include unpredictable nature, resistance to plain text attacks. So the combination of both will provide the advantages of authentication along with chaotic advantages. So the algorithm will be highly secure, it will be resistant to both the types of attacks and will provide very large key space. The limitations of previous research work includes for AES implementations, resistance to attacks are not included. The chaos-based methods are basically implemented on medical grayscale images, so the color image encryption is not included. Chaotic encryption does not include authentication. The initial conditions of chaotic maps does not depend on input image, which makes the system weak against differential attacks, loss of image attributes, and if the histogram of encrypted image is not uniform, then the security against statistical attacks will be hampered. The research contribution of presented work includes the authenticated block cipher encryption along with the chaotic improvements. The randomness is increased. Secret keys will be generated using chaotic maps. Initialization vector will be generated using maps. The addition of 128-bit key. Original substitution box of AES will be shuffled. The obtained results will be analyzed, so the system is robust to various types of attacks and the system is able to encrypt the color images. Galva counter block diagram is shown over here. It includes the AES encryption of initialization vector concatenated with the counter, and the output will be XORed with the original image. Galva hash generation will be used for authentication where cipher, length of cipher, additional authentication data and its length will be divided in 128-bit blocks and it will be multiplied with H. H vector is the AES encrypted output of 128 zeros. The chaotic sequence will be generated using hyperbolic tangent map, and this random sequence will be XORed with the input image to increase the randomness. The algorithm includes the reading of color image, generating the vector, converting the values to bits, initializing the chaotic keys, and applying hyperbolic tangent map to generate the random bit stream, which will be XORed with the input image. So the final block diagram of authenticated encryption is shown over here. As seen, the GCTR is the basic block. As box is shuffled and applied to GCTR, input color image will be XORed with the random bit stream and applied to the block. Input color image attributes will be used to generate the chaotic initialization vector. And finally, the cipher image will be generated. Also, the final output generated will be the authentication tag, which will be verified on the receiver side. The basic key of AES will be generated using Robust Renyi Modulo Map. Initialization vector, which is of 96 bits, will be also generated from original image. AES basic S box will not be used as it is. It will be shuffled using modified Arnold cat map and used for AES encryption method. This figure shows the MATLAB simulation. Now the results are presented. The simulation using MATLAB is presented over here. Different statistical parameters includes first of all the information entropy. It is the statistical parameter used to analyze confusion and randomness. It is having maximum value of 8. So the results indicate that the results are close to maximum value 8. This demonstrates that deriving the actual picture from the encrypted image is challenging. Maximum deviation indicates the difference in pixel values between two images. So for efficient encryption system, plain and cipher images should be entirely different. So maximum deviation should be high. As seen, for encrypted images, maximum deviation value is very high. Mean square error evaluates the avalanche effect. It indicates the ability of the algorithm to generate substantial difference in cipher image even if a little alteration is made to the key or the input image. Also, for the decrypted image, the values are 0. The frequency test is suggested by NIST, where it measures the randomness in the encrypted images. For successful encryption, the p-value should be greater than 0.01. Thus, the available values indicate that the algorithm is producing the encrypted image with the truly random sequence. So, our algorithm is passing this test. Peak signal to noise ratio. Infinite values for decrypted images indicate that the original images are correctly reconstructed at the receiver side. Structural Similarity Index Measure SSIM compares two images based on three important parameters: contrast, luminance, and structure. Its value is between 0 and 1. So the value close to 0 represents that the original and encrypted images are much different. Correlation coefficients. This is the statistical tool which measures the strength of linear relationship between adjacent pixels. So the value range is between -1 and +1. So to resist the statistical attacks, the adjacent pixels should be weakly linked. Thus, the suggested encryption method complies with zero correlation criteria and offers the strong resistance against attacks based on correlation. As seen from the visual correlation for Lena image, the graphs of plain images have the concentration of values in the specific regions. The graphs for cipher images are scattered. Thus, our approach breaks the significant dependence between adjacent pixels and makes the cipher hard to break. The histogram analysis is presented. The intensity of pixels in graphic is displayed using histogram. The histogram of actual input image shows concentrations of pixels at specific levels, but the histograms of encrypted images are uniform, which makes the system more robust and difficult for an opponent to decipher. The comparison of results for paper image with the previous research work is presented. Thus, the higher values of entropy and much lower values of correlation coefficients indicate that our system is providing high security. For Lena image also, the comparison is done. Thus, the entropy is higher as compared with the previous. The major issue with the hybrid chaotic methods is to maintain the picture attributes lost in the decryption. For decrypted image, for the proposed method, we are getting PSNR is infinity, maximum deviation is 0, MSE value is 0, SSIM is 1, and correlation coefficients are also close to 0. So the conclusion from this results is the image is correctly reconstructed on the receiver side. For cipher images, the SSIM value is extremely close to 0, PSNR is less than 10 dB, MSE is also very high, and totally different histograms are obtained for encrypted images. Thus, the security against statistical attacks is proved. Also, the chaotic keys are depending on the original image. So, the conclusion will be that the algorithm is secured against differential attacks. Previous research focuses on medical grayscale images, but the proposed algorithm is useful for color images related applications also, and the results are in agreement with the results of previous research works. The conclusion is image encryption combining chaotic sequences with improved AES GCM is presented. The sensitivity to initial conditions and control parameters is obtained. The higher security along with authentication. The system is also tested using statistical security parameters, which indicates the security against differential, statistical, and brute force attacks. The future scope includes combining error correcting codes with chaotic encryption to enhance the performance. These are the references which are being referred. Thank you.